Another example, here I have I can't use this clock. Smoothly between the seconds. And digital. And obviously, we can think of many examples of why the world is analog all over the place. But why are computers digital? They don't actually have to be digital. There are actually some examples of analog computers. And here's a picture of one. It's very old. It's from about 1960. It's called the Heathkit Educational Analog Computer. And what you do with this computer And what do I mean by extreme? So, digital is all about restricting the values that you can take. And if you restrict the values you can take in an extreme way, so that you can only have one of two different values, well, if you do that, then you can build your computer entirely out of switches. Because a switch is something that's either on or off. Open, so no current is flowing, or closed, current is flowing. Switches are very cheap, very efficient, and it's very difficult to misinterpret. You only have to be able to spot the difference between current is flowing, current is not flowing. Whereas with that analog computer, I'm sure you could imagine a whole lot of anxiety about is this sharing 51.7 volts or is that 51.8, 51.9? It's hard to be truly accurate in an analog setting like that. Of course, the obvious problem we have is we've only got two values. It's not very useful, right? I mean, if you could only say your height is this high or this high, and that's the only two options. And it's not going to be very sensitive, is it? So how can we tackle that problem? Well, basically, you need lots of switches. And what you need to combine those lots of switches with is the binary counting system. So I just want to say a few words about that. You've probably come across the decimal counting system once or twice. In the decimal counting system, you have 10 different digits. They go from 0 all the way up to 9. And when you count, you go from the 0 through to 1, 2, you go through all of the different digits you have until you run out of digits, which happens around here. And when that happens, you have to go to an extra column, the tens column. You put a 1 in that column, and you go back to 0 in the units column. And then you carry on like this. Now, you've probably done this yourselves once or twice at home. The binary counting system is actually very similar. The only difference is that rather than having 10 different digit symbols available, you only have 2. You only have 0 and 1. So it starts the same, goes from 0 and then 1, and then you run out of symbols. So at this point, you have to jump straight up to 10. Okay, and then we can carry on, so we can go to 11, and then again, we run out of symbols. And so at this point, we have to jump all the way up to 100. And then we carry on like so. And so eventually, once we get to something like 9 in decimal, in binary, that's 1001. So you can see these binary numbers, they get very long very quickly. There's not much variation within the number itself. They're all just zeros and ones, but they do get very long. So what can we do with this? Well, we can make a mapping between these binary numbers and a bunch of switches. And this mapping is easier to see if I just add in the leading zeros. So I can always add zeros in front of a number without changing its value. So I'll do that. So now all of these binary numbers are 4 digits long. And so if I have 4 switches available, I can represent these numbers. So for instance, to represent 0, 0, 0, 0, I will use 4 switches and I'll have all 4 of them open. To get 0, 0, 0, 1, I'll have open, 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 and closed. And so on. So the zeros correspond to open and the ones correspond to closed. So with 4 switches, I can represent a whole load of digital values. Okay, so we've got around the problem of only having 2 values just by having lots of switches. And this observation really is the basis of the digital computer revolution. Okay, we're now ready to start the lecture properly and look at how we convert from digital signals, so a bunch of these values represented by switches, so you've either got current flowing or not flowing, into an analog signal like we saw on that analog computer, where the value of the value that we want to represent is proportional to the voltage on that wire. I just have one more tiny bit of background, which is I want to show you a thing called a demultiplexer. Demultiplexer, a big word, is quite high scoring in Scrabble, commonly abbreviated as demux. A demux is a pretty simple component we're going to make use of, and what it does is it has one wire coming in at the top. It has 2 wires coming out at the bottom called out A and out B, and it has another wire on the side called the control. And what happens is if you put if you put a low value on the control wire, so you don't have current flowing there, then what happens is any signal that comes in at the top will be sent to the right-hand output. And if you put a 1 on the control wire, then any signal that comes in at the top is going to be sent to the left output. Okay, that's all it does. Okay, now we're genuinely ready. So what I'm going to show you is a 3-bit digital to analog converter, DAC, digital to analog converter. And it's 3 bits. Bit is just short for binary digit, by the way. It's 3 bits because I have 3 input wires on the left coming in. This is holding my digital signal. So each of those wires is going to be high or low. And on the right, I have the output of my digital to analog converter. And basically what I want is I want to be able to put a value in. So for instance, low, high, high, so 0, 1, 1. Remember from that table, 0, 1, 1 is in the binary representation of 3. And so in this circumstance, I would like my DAC to produce 3 volts on the output. Okay, so how are we going to build it? Well, the basic component that I'm going to need is a string of resistors. So what I've got here is I've got a voltage source of 8 volts, carefully chosen. It goes through a series of 8 identical resistors and then finishes at ground, so 0 volts down here. Now, because all of these resistors have the same resistance, say R ohms, doesn't matter what the resistance is, just as long as they're all the same. because they've all got the same resistance, they're all going to drop the same proportion of voltage, which means that after this resistor, I'm down to 7 volts. Down here, I'm down to 6 volts. Down 5, 4, 3, 2, 1, and I'm down to 0 volts, which is ground. Okay. And then I'm going to pull off a wire between all of these resistors like this. And I'm going to put a switch on all of these wires. And it will become apparent in a moment why I've drawn these switches in a diagonal like this. I'll bring them all together like so, and going to the out. So now what I'm most of the way there, because you can see, to take that same example again, if I wanted to, if I had an input that was, say, the value 3, then all I need to do is work out how to close switch 3 here, because then I will drop the 5 volts there. I'll have 3 volts left, which will come along here and go to my output. So all I need to do is work out the correspondence between these 3 wires coming in here and these 8 switches here. And to do that, I can use my demultiplexers, which I arrange in a tree like this, a kind of upside down tree. So at the top, I have a constant current coming in, and I connect my inputs to the side of these demuxes, the sides that control which way that current is going to flow, like so. So this will all become clear once I do an example. Let's suppose the input is the binary representation of 3, so 0, 1, 1. What's going to happen is I have some current coming in here. The first demux is being controlled by a 0, which means it's going to send the signal to the right. The second demux is going to send the signal to the left because it's being controlled by a 1. And the third demux is going to send the signal to the left again because it's controlled by a 1. It comes down this wire. We hit switch number 3. Bosh, closed. And et voila, we have 3 volts coming out, which is exactly what we wanted. I'll just do one more example. Suppose we have 1, 0, 0 coming in here. So that's the binary representation of 4. So the first demux is going to send the signal this time to the left. The second demux is going to send it to the right. The third demux is going to send it to the right again. And there we are. We've hit switch number 4. Bosh, closed. And thus we get 4 volts coming out. So that design seems to be working pretty nicely. It's a very old design, actually. It was devised by Lord Kelvin back in the mid-19th century, of all places. It was first implemented in a sort of electrical setting in the 1920s. They used resistors and mechanical relays. It's sometimes called the thermometer DAC, perhaps because of Lord Kelvin's work on temperature. It's a simple design. That's partly why I chose to bring it up in the lecture now. I mean, for one thing, it only needs one type of resistor. But you do need quite a lot of those resistors. So just for my 3-bit DAC, I needed 8 resistors in a long chain. If I were to do a 10-bit DAC, so that could take 10 wires in, I would need over 1,000 resistors in my chain, which is it's getting quite long. So in practice, this kind of DAC is only really useful for quite low, maybe up to medium resolutions. Maybe you'd manage up to about 10 bits or so, and then you'd want to use a different design of DAC. And there are many more advanced designs for DACs. And well, I suppose this is the point when I say, you should come to Imperial and you'll learn about all these different advanced designs of DAC that I don't have time to tell you about today. Although this design of DAC is in the modern world. So for instance, you could use a quite low resolution DAC like this for controlling on your phone. You've got a whole load of pixels on your screen. You need to adjust the brightness of each pixel so that you get the right overall picture. You need to do this very quickly so you can watch a high resolution video. And you could use a DAC behind each pixel to convert the digital signal coming from the processor into the appropriate voltage to make the pixel the right brightness. So, yeah, chances are you have something like this in your pocket right now. Okay, so that's the first part of the lecture. That's digital to analog. This is how you can go from the computer into something that the humans can understand. But the other direction we're going to consider now, and that's how can we get information from our analog world into a form that the computer can understand. So that's ADC, that's analog to digital conversion. The specification for this problem is as follows. We want to be able to supply an input voltage here on the left and produce a digital signal on the right that corresponds to that. So if, for instance, if I were to have 9 volts coming in on the left as an analog voltage there, I would like these 4 wires here to have high, low, low, high. So 1, 0, 0, 1, which, if you remember that table, that was the binary representation of 9. Okay, so how am I going to build this? Well, the simplest design is actually it's a little bit like the DAC that I just showed you, kind of in reverse. But that's not so interesting to go over that again. So I'm going to show you a different design that's based on this thing here called the successive approximation register, which sounds terribly fancy. But I'll show you how it works. So first thing to note is this is going to be a 4-bit ADC. The DAC that I showed you was only 3 bits. Now we're going up to 4 bits. And the ideas are all the same. It's just a bit bigger. So what do we see here? I'll show you what this sample and hold does in a moment. We have a comparator component here that's able to take 2 wires in, and it's able to work out which wire has the higher voltage and then behave differently depending on which wire is higher voltage. We've got some control logic for controlling what goes on. This is the successive approximation register. The output wires are being tapped out from these 4 wires here. And here we have a 4-bit version of the DAC that I just showed you. So this is why I've done the lecture this way round, because you're actually using a DAC to build the ADC. That's kind of cool. So, okay, let's do an example. What I do to begin is I load my successive approximation register with the value 1, 0, 0, 0. That's the binary representation of 8, which is quite nice because 8 is bang in the middle of the range of possible values. Okay, you see the smallest possible value that I might be producing is 0, 0, 0, 0, which is 0. And the biggest possible value that I might be producing is 1, 1, 1, 1, which is 15. So I know that my output value is going to be somewhere between 0 and 15. And so 8, which is pretty much in the middle, seems like a pretty reasonable place to start. And basically what we're going to do is we're going to successively sort of get closer and closer to the right value. Okay, so if we've got 1, 0, 0, 0 to 8 in this successive approximation register, we're feeding this into the 4-bit DAC. Now we know what the DAC does already because we've seen it. This DAC is going to produce 8 volts on this output wire here. So that 8 volts comes here. Okay, now let's pick a value for our example for the voltage in. Let's say our voltage in is 9.4 volts. Okay, first thing that happens is this 9.4 volts goes through the sample and hold component and comes out on the other side. The point of this sample and hold component is we're going to take a little while to work out what the output should be. And we're going to have to do a couple of loops around this circuit here. And while we do that, we don't really want the input voltage to be fluctuating all over the place. That would be very confusing. We want it to hold steady just for a few cycles. And that's what the sample and hold does. So here, this voltage now is free to change however it likes, but this voltage here will stay constant. Next, we come to the comparator. We have 8 volts coming in on this wire, 9.4 volts on this wire. So the comparator says, top wire has higher voltage. And what the control logic then does is it says, okay, what that means is that this 1 is correct. So it colors that green, at least conceptually, colors it green. That 1 is now confirmed. And it moves on to the second digit in the successive approximation register. It sets it to a 1, and the process repeats. So now, coming into the 4-bit DAC, we have the number 1100, which I can tell you is 12 in decimal. So that means the 4-bit DAC is going to produce 12 volts on this wire here, which will be compared against 9.4 volts. This time, 12 is bigger than 9.4. So the comparator will notice that, and it will tell the control logic. And the control logic says, okay, well, that means this 1 is incorrect. That shouldn't be a 1. That should be a 0. We've gone too big. Okay, so the 8 was too low. We need to go up a bit. The 12 was too high. We need to go down a bit. So we switched this 1 down to a 0 and confirm it. It's gone green. We move on to the 3rd digit. We set it to a 1 to begin, and the process repeats. So now we have 1010, which in decimal is 10. The 10 signal comes into the 4-bit DAC, is converted into 10 volts, goes around to the comparator. Comparator compares the 10 volts against the 9.4 volts. 10 volts is bigger, again, so the bottom wire is bigger. So the control logic says, okay, well, that 1 is also incorrect. Okay, you've gone too high again. So that 1 is downgraded to a 0, colored green, and we move on to the final digit. So we set that to a 1, and the process repeats. We now have 1001 coming into the 4-bit DAC. 1001 is 9, so the 4-bit DAC will produce 9 volts. 9 volts is less than 9.4 volts, just a little bit. So the control logic will say, that means the 1 is correct. At this point, the process is complete, and we can read off the values on these 4 output wires, which will be 1001, which is exactly what we wanted, 9 volts. Okay, so the ADC is rounding down, I should point out. So you always lose a bit of information when you do analog to digital conversion. You lose this 0.4 volts. But what can you do? That was fairly complicated, so let's just do one more go round that. So let's pick a different value. So again, we'll start with our successive approximation register set to 8. So the first digit is the only one set to a 1. The 4-bit DAC is going to produce an 8 volts on its output, and we're ready for a new voltage to be supplied as the input. Let's pick a different value. Let's say 5.5 volts this time. So again, we're rounding down, so we're expecting the output to be the binary 5. So sample and hold to hold it steady at 5.5 volts. Okay, so compare 8 volts against 5.5 volts. 8 volts is bigger, so the control logic says this 1 was incorrect, needs to go down to a 0, and we confirm it. We set the second value, the second digit now goes to a 1, and we go through the 4-bit DAC again, 0100, that is 4 in decimal. So 4 volts will come out here. 4 volts is less than 5.5 volts. So that means the control logic will say that the 1 here is correct and it will be confirmed, colored green. We move on to the third digit, set it to a 1, and the process repeats. 0, 1, 1, 0 is 6 in decimal. So we have 6 volts coming out of the DAC. 6 volts is bigger than 5.5 volts. So the control logic says, no, that 1 was incorrect, needs to go down to a 0, confirm it by coloring it green, and we move on to the final digit, setting it to 1. 0, 1, 0, 1 is 5 in decimal. That comes to the DAC. We produce 5 volts coming out. 5 volts is less than 5.5 volts, which means the control logic says that this final 1 was correct. And so we're ready to read off the output 0, 1, 0, 1, which is 5. It is working correctly. So this 4-bit ADC that we produced, it takes 4 cycles. Maybe I had to go around that loop 4 times to convert just one sample, which, compared to some other designs, is not bad at all. Actually, that's considered quite quick. It's a simple design, still a bit more complicated perhaps than the DAC, but still pretty simple. And again, compared to some other designs that I haven't shown you, it's pretty low power consumption, which is nice. And you can get this design working perfectly nicely up to about 16 bits. Okay, so you could cope with 16 output wires coming out, and above that you'd probably want to use a different design. And again, ADCs they're all over the place. In microphones, you take an analog audio signal coming in. You need to convert that into digital, so you can record yourself on your phone. You need an ADC for doing that. A webcam, digital camera. All these things, you're taking analog information about the brightness of the light hitting various parts of the webcam. You need to convert that into a digital signal again. So the devices like this, you may have hundreds of millions of them in your pocket. That's pretty cool. And just like with the ADCs, there are many more advanced designs that are clever in all sorts of different respects. And, well, you should come to Imperial and learn more about how those work. Okay, so this is more or less all I wanted to tell you. That was the first part was going from digital to analog. Second part was going from analog to digital. And if I were to just give a quick summary of some of the key points that we've talked about, told you about analog and digital. Said that analog was more or less means continuous. Digital basically means discrete. We noted that digital computers are made out of lots and lots of switches. And if you have enough switches, you can encode numbers using the binary counting system. We saw a design for digital to analog conversion that used a chain of resistors and a tree or upside down tree of demultiplexers. And we saw a design for analog to digital conversion that used this successive approximation register. Which sounds terribly fancy, but as you saw, not really that complicated.
That's great. Thank you so much, John. I found that really, really interesting, and so did the audience who would like me to kind of address any questions that you have. But yes, we'll get straight into those because they are coming in at the moment. But thank you so much, John, for that. The first question that we've had.
Shall I stop sharing my screen, perhaps?
Yes, that would be great.
There we go. I think that's done it.
So the first question that we've had come in is around, are quantum computers designed to be analog or digital?
Yeah, they're more analog, aren't they? They're yes. What can I say concisely about that? Yes. So quantum computers would be a good example of an analog computer. I think the what they call the qubits that they're made of can take a continuous range of values, and yes, they're enormously powerful, and there's enormous interest in them in both from the sort of hardware designers who are actually building these quantum computers, but there's a lot of work in the programming languages field where I work in how you can write programs for quantum computers. So we're kind of tackling the problem at both ends, both how you build the quantum computer and how you build programming languages and programs and compilers for quantum computers. It's very exciting.
I think that's, I mean, with this topic that you introduced, as you said, and it was great, you know, one of the reasons you may want to come to Imperial is other layers and depths. And I think some people are putting in questions about that kind of knowledge and what they can do to kind of prepare themselves to explore this at a deeper level. Do you have any kind of recommendations for students who are, you know, curious about this and what they can do as, you know, high school students in preparation for exploring this at university?
Well, I suppose a well-chosen textbook it can be very inspiring. Actually, I remember reading a book called the Turing Omnibus. I think it was by, if I remember right, it was by A.K. Dewdney. You'll find it on Google. And that was great because it kind of took I think you described it as like a whistle-stop tour of some of it. It basically just picked out some of the more interesting nuggets of it was mainly computer science, and it explained them. It was just the right level for me at that time, and it was I probably read it in around year 12 or so. And in fact, I remember it had analog computers. That's the one. Yep. It had analog computers in, a bit like what I talked about in my lecture. In fact, it had this observation that to build an analog computer, you don't even need electricity. So all of the computers that I talked about in my lecture, they were very, you had to plug them in. But you can still be a computer without having to plug in. So for instance, very few of you maybe have heard of a slide rule, which is this kind of gadget that you can use to do multiplication just by sliding it looks a bit like a ruler, and you slide part of it out, and then you look at the readings on it, and you can see how to multiply, see the result of multiplying two numbers. So it's an entirely mechanical calculator. But as a computer, it's computing something. It's not using electricity, but it's computing. The example that they gave in this book, if I remember rightly, was how to sort some numbers using spaghetti. And what the problem is you've got a whole bunch of, say, 100 numbers, and you want to put them into ascending order. What you do, you buy some spaghetti, hard, dried spaghetti. You take a piece of spaghetti and you chop it to the length that corresponds to each number in turn. So if the numbers are 5, 6, 7, 4, you take your spaghetti and you cut it to 5 centimeters, 6 centimeters, 7 centimeters, 4 centimeters. Then you gather up all of these different lengths of spaghetti and you bang them down on a table. And then you just look at which is the spaghetti that's poking out at the top, pull that out, lay it down, take out the next one, pull it out, lay it down, and so on, until you've got no spaghetti left, and it's sorted. So that's how you could, and that's a computer, because you're not. That's entirely mechanical process, no thought required. doing the thinking for you.
That's brilliant. Yeah, so I did put the book in the chat, and we have had questions around, books that you could recommend. So yeah, do take a look at that. Some more questions coming in. So during the ADC example that you shared, we had a question about, does that mean that the output will fluctuate a lot of times before the successive approximation register actually gets it somewhat right?
That's a nice question. Yes, so the successive approximation register was starting at 8, and then it was sort of going a bit over and then a bit under, and then eventually it was settling on the right value. So yes, that as drawn, you would be able to see the output, exactly as you say, fluctuating. So I guess you have a couple of options. You could just say, you could give an instruction to whoever is using your ADC to say, make sure that after you've supplied the input, make sure you wait, in this case 4 cycles, until you look at the output. And if you choose to look at the output too early, that's your fault. Or perhaps a slightly kinder design would have an extra component that basically has a switch that just says that basically only opens when after 4 cycles. So you just can't, it hides the output until the correct output is there. That's probably a more realistic way to do it, isn't it?
And during the same example, how does the successive approximation registers initial conditions, so 1,000 in this case, matter? It seems that there is no performance penalty if we choose any arbitrary starting condition.
Oh, what a nice question. Wow. So do you have to start at 1,000? Will you still get the right value if you start? Let me think. So let's suppose an extreme case would be if you start your successive approximation register at 0000, but the correct value that you should be aiming at eventually is 1111. So will it still work? Feels like that should still work, doesn't it? Because the 0 will be deemed too low and upgraded to a 1. And then you'll do 1000, which is still too low, so that would be. I suppose you'd need. It's a really good point. I suppose you'd need slightly different circuitry in the sense that in my design, the only things that could happen are you have a 1, which is confirmed, so it doesn't change, or it gets downgraded to a 0. So the only transition that's possible is 1 going down to a 0. Whereas, and then I suppose if you were to do it the other way around, so starting at 0000, then it would just be slightly different, wouldn't it? You would be going from a 0 up to a 1 or confirming the 0. Yeah, that's a really nice point. I think it really does seem. I think, okay, so my concise answer is I think you're probably right. It doesn't matter. I think it would be perfectly nice to start at 0000. You would just have to make sure you're consistent, that you always start at 0000 or always start at 1000, because otherwise you'd have to be able to go up or down, and that might make your circuit more complicated than it should be. Yeah, very nice question.
Great, thank you. Another audience member has asked, is this process approximating the binary value of that voltage?
Yes.
That's nice and concise there. And going through some of the, what is a transistor? Is it used for DAC? Is it used for DAC or DAC or the other ADC?
Yes, so I didn't use the word transistor in the lecture, but basically every time I used the word switch, you can more or less replace that with transistor. So a transistor is a kind of electronic switch that's activated by putting some current onto the bit that closes the switch. They're terribly efficient, and they really led to the whole digital computer revolution. In that very early design, I mentioned relays, so these mechanical relays that sort of physically move to open or shut. But yeah, once you worked out how to do a completely electronic switch with no moving parts, so the transistor, yeah, that's where things really got going.
And you mentioned in the lecture that about the ADC always rounding down the values. Can they round off values instead of only rounding them down?
Very nice question. Yes. Could you change it so that you always round to the closest? Is basically what you're saying. Yeah. Well, I suppose, I mean, it may be a slightly silly, a slightly trivial answer to that would be, I think if you were to just subtract 0.5 from your input to begin with, I mean, that would add, if you add, let me think, wait, so it's 9.7, yeah, if you add 0.5 to whatever your input is, and then use the rounding down approach that I already showed, and then maybe subtract 0.5 again from the output. I can't quite do the mental arithmetic in my head, but I feel like if you were to add on a bit of adding and subtracting of a half, you'd be able to mimic whichever rounding scheme you wanted.
Great, thank you.
Can I just follow up a slightly bigger picture on that one, I suppose, because it's a very good question. But I guess in reality, I mean, if you think about where these components are used, say in a microphone, for instance. So you're listening to some analog audio signal and you're converting that into digital. Once you've got enough bits, then whichever digital value you end up with, the likelihood is that you're going to be pretty close to that analog signal anyway. And so the matter of whether you're rounding, whether this 0.6 goes down or goes up, like, I'd say it doesn't matter too much as long as your resolution is high enough. You're not going to hear the difference, I think.
Great, and I can see, this has obviously sparked a huge amount of questions. So we will try and get through as many, but I am conscious of time. But with that, we have another question. So why is hexadecimal values, do they seem prevailing and commonplace in electronic designs? What makes the hex values work particularly well within a binary system?
Very nice. Yes. So I didn't use any hexadecimal values in this lecture, but they certainly do appear a lot. So I showed you decimal, which is where you have which is the number system that's based on having 10 different digits available, 0 up to 9. Showed you binary, which is based on having 2 different digits, 0 and 1. You've also got octal, which is 0 up to 7, so that's 8 different values. So you'd go 0, 1, 2, 3, 4, 5, 6, 7, 10, 11 as well. Yeah, and then hexadecimal. So hexadecimal is base 16. So that there you'd count. First, you need to invent 6 extra digits, and we tend to use A, B, C, D, E, and F there. So the way you'd count in hexadecimal would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F. Sorry, I said 10, didn't I? Try again. 1, 2, 3, 4, sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then 1A, 1B, and so on. Okay. So why is hexadecimal nice? The thing is, converting between decimal and binary doesn't actually, it is kind of fiddly. It's because 10 is not a power of 2, more or less. Whereas base 16 is a power of 2. And so what it means is that every 4 binary digits translates directly to 1 hexadecimal digit. And so converting between binary and hexadecimal is really, really easy. But hexadecimal doesn't have this problem that you saw with binary, where the numbers were getting terribly long very, very quickly. In fact, hexadecimal numbers are even shorter than decimal numbers. So that's their use.
We have some more specific questions, but there is one that has come in around the other topics that you cover in a triple E major. What do you learn, and what kind of careers do triple E majors go on to after university?
Well, so what else do you learn? I was talking yesterday to a lecturer who teaches about electromagnetism. So that's certainly one that crops up. You do programming. So programming is increasingly important as electronic devices and hardware and so on become increasingly complicated, and you need to program them at higher and higher levels of abstraction. So there's quite a bit of programming. There's a lot of maths, both discrete maths, so digital maths and so on, but also continuous or analog maths. It's a lot of that. We have very popular courses on robotics. We have there's a lot of stuff on signal processing. So, for instance, we have some lovely work going on in the department that's about understanding the relationship between electronics and sound, and sort of advanced microphones and advanced speakers. So, for instance, there's one project going on that's to do with can you use, you know how if you have a really big speaker, you can make a really loud sound, but can you make just as loud a sound by using lots and lots of little speakers and just timing it perfectly to just make a real poof. So yeah, there's a bunch of stuff to do with that going on. Lots of machine learning. That's a very fashionable topic these days, and we have lots of courses about that. As for careers that you go into, so I guess a lot of people, well, let's see, some people go and work for a startup, and I've students who've done projects with me and gone on to set up startups. A lot of them go and work for tech companies. A whole bunch of them go on to ARM, for instance. It's a popular destination. Indeed, quite a few students during their degree go and spend a summer working at a company like ARM. And I'm one of the people who supervises the students while they do these placements. Some go and work in finance, in banking, and so on. Some go and work for traditional engineering firms. Yeah, that's probably a reasonable cross-section. Yeah.
I think the skills that you learn can be applied to so many careers, and yeah, as you say, some students will choose to go into research or startups. There's a huge amount of support that Imperial offers in terms of entrepreneurship and applying those skills. So yeah, what you're learning can really be applied across a wide range of sectors, as you've kind of highlighted from what students are going on to. Just going back to some more questions regarding what you were speaking on today. Someone said, I wonder whether volt is a representative of a real-world analog signal, or all analog signals are converted to voltage in advance.
Yes. I was kind of assuming that, yes, I'm assuming that you'd already found some way of converting whatever analog signal you were interested in into some voltage. And so again, just going back to that, the audio example, you could imagine a traditional microphone takes the sound wave, which shakes the diaphragm, and the diaphragm, then you got a mechanical link between that shaking of the diaphragm and the adjusting of the voltage on the wire. And so I'm starting from that point onwards. Yeah.
Great, thank you. And why is 0 on the highest input digital and 2 on the lowest input digital in the example of DAC? Should it not the Q2, Q1, Q0 for the highest to lowest digital input in the case of the DAC?
Q, trying to remember where the Q came in. Oh, it was in, because I had in 2, in 1, in 0. I think I had it the right way around, but I mean, there are no guarantees. It's the easiest thing in the world to get these binary numbers the wrong way around, especially when I'm sometimes writing them this way around, sometimes writing them like that. So yeah, I would say it's entirely possible that I had it the wrong way around, but yeah, hopefully the overall ideas came through.
Is it all? Is that all computer basics on DAC and the ADC?
Is that all computer
basic? Maybe if this person wants to clarify that question, we can look at that. Another one. So, how does a successive approximation register physically work?
Okay, so the physical implementation of the register. So I guess to implement, okay, so a register I would think of as a little component that is capable of storing some, let's say, storing some current for a bit. So that you can then look at it later and see what value it's holding. And a standard design for this is you kind, again, without wanting to go into too many details, but you kind of set it up so that you build a little looping circuit that sort of keeps propagating the value going around in a circle, and that means on, that means 1, or you kind of turn it off, and then that stops the current going around, and that represents the 0. So that's very, very roughly the kind of thing, and you'd use that for each of the 4 bits in that register. Yeah, I think that's about the level of detail I can manage.
Right. So we just, I'm going to finish off today's session with just a kind of, we've had a couple of questions around this area, but I do want to say a massive thank you, John, for that lecture. It was really, really interesting, and we have had a lot of questions come in, and sorry if we haven't been able to answer your question in this time. But the final question that I want to ask you is 2 questions that are kind of together. As people have asked, what can I do to prepare academically before coming to Imperial? And any other recommendations of books or articles that students could explore? There's quite a few questions around what they can do to kind of preparing for a university like Imperial.
Yes, these are good and important questions. So I stand by my recommendation of the new Turing Omnibus. I think that is a good one. I am aware of other textbooks and so on that I have enjoyed and found very influential, but I guess I suppose that one has to be a little bit cautious about it sometimes, because I'm conscious that I think I read some of these textbooks maybe a year or 2 after I started my undergraduate, and what I wouldn't want is recommending textbooks that are too advanced too soon, because I think that can be disheartening for no good reason. I think so. In terms of other resources, I'm a big fan of Wikipedia. I think a lot of the articles on these topics on Wikipedia, I think, are very accessible. I think there are some great YouTube videos explaining some things along these lines. So I think those are pretty good. Then other things to prepare, I suppose. I suppose probably the best thing you can do, other than consuming material from Wikipedia and YouTube and these textbooks, is I guess fostering an enthusiasm for the topic, and I think you can do this by doing sort of self-driven projects. Not necessarily with any particular achievement in mind, but just enjoyment. Following your curiosity. I remember when I was in probably this sort of level, I got quite into programming. I remember making little games for programming. Trying to remember some examples now. I mean, it's probably completely changed nowadays, and you can probably make much more advanced games than I was managing. But I remember, I made board games. I think I made a Scrabble player. Was one of the projects. In fact, I took that to an online Scrabble playing online competition thing, and used it to get a very high score, which I'm not sure retrospectively was allowed or not. But anyway, so I think doing some fun projects, because enthusiasm is really going to drive you through your degree. You need to be enthusiastic about your topic, because no matter how good you are at the topic, it's gonna be hard at various stages.